Most companies already have SharePoint. They have the documents. They have the AI licenses. But the moment someone asks a specific question, the AI comes up empty. It isn't because the data is missing. It's because the data isn't connected. That's the exact problem we're solving today. We are building a private RAG system from the ground up. We'll use SharePoint as our source and n8n as the central brain. We're bringing in Mistral OCR to act as the eyes and a vector database to serve as the memory. And before we dive into the build, make sure to subscribe to the M365 FM podcast. Every single episode is a deep dive just like this one. What RAG actually is. Most people define RAG as giving AI access to your documents. That is the surface level explanation. It isn't technically wrong, but it skips the one part that actually makes the system work. Here's the real model. A retrieval layer sits directly between the user's question and the language model. This layer has one specific job. It has to find the right content and hand it over to the model as context. The model itself never goes searching through your files. It doesn't read SharePoint. It has no idea your folder structure even exists. It only reads what the retrieval layer chooses to give it. That is the boundary. Everything above that line is generation. Everything below it is retrieval. These two processes have almost nothing to do with each other. When a RAG system fails, when the answer is wrong or it starts hallucinating, the problem is almost never the language model. The real issue is that the retrieval layer failed to hand over the right information. This is the structural insight that most teams completely miss. They try to fix the problem by upgrading the model. They switch from GPT-4 to something newer and more expensive, but nothing actually improves. The model was never the bottleneck. The retrieval was. So, what does this retrieval layer actually look like? It's made of three components. You have a document store, a vector index, and the language model that generates the final answer. The document store is where your source files live, which for us is SharePoint. The vector index is where the actual meaning of those documents is stored as a series of numbers. The language model sits downstream of both. It only sees what the vector index decides to return. That word, meaning, is doing a lot of heavy lifting here. We need to be very precise about what that looks like in practice. When you convert text into a vector, you are turning it into a long list of numbers. Those numbers represent where that specific thought sits in a mathematical space. If two sentences mean the same thing, their vectors will be mathematically close to each other, even if they don't share a single word. A phrase like revenue declined in Q3 and another saying sales dropped last quarter will sit right next to each other in that space. A standard keyword search would miss that connection entirely. This is why vector search is fundamentally different. Keyword search asks if a document contains a specific word. Vector search asks if a document contains the actual idea. That distinction is the entire reason RAG exists. The gap between finding a document and actually answering a question is massive. A question isn't just a keyword, it's an intent. It comes with context and assumptions. Standard search cannot bridge that gap because it returns files, not answers. RAG bridges it by turning the question into a vector and comparing it against your stored data. It pulls the most similar content and hands it to the model. The quality of your answer is a direct result of the quality of your retrieval. If you get the retrieval right, even a basic model will perform well. If you get it wrong, no model on earth can save the output. That is the foundation. Now, let's look at why the standard approach usually breaks before it even gets started. Why standard search fails. SharePoint search works exactly the way it was designed to work, and that is precisely the problem. The system was built for a very specific mental model where the user already knows roughly what they are looking for. You type a word or a phrase, and the engine returns a list of documents containing those exact characters. It is fast, it is indexed, and it scales across massive document libraries without breaking a sweat. For that one specific task, it performs well. But that mental model is broken. It is not just failing occasionally, it is failing structurally. Every keyword-based search system relies on the assumption that the user's vocabulary will match the document's vocabulary. It assumes that when you are looking for information, you already know the exact words the author used to describe it. In a world where people spent their days navigating menus and clicking through folders, that assumption held up reasonably well. Work does not start that way anymore because today, everything starts with context. You might be in a meeting and need a specific number, or perhaps you are onboarding and need to understand a complex process. You could be drafting a proposal and need to know what was agreed upon 6 months ago. In these moments, you are not searching for a file, you are asking a question. The problem is that your question might not share a single word with the document that contains your answer. Keyword search has no response to that reality. It only returns what matches the literal words, so it cannot infer what you actually mean. It does not understand that Q3 performance and third quarter results are the same concept. It certainly cannot synthesize a single answer from content that is spread across 3 separate files. Vector search solves this vocabulary mismatch by mapping meaning instead of characters. 2 phrases that mean the same thing end up in the same neighborhood of a semantic space, even if they look nothing alike on the surface. When a user types a question in natural language, the vector search looks for matching meaning rather than matching words. But even that level of intelligence is not enough for every question. Consider a real example from this system where a user asks for the company's total revenue in 2024. That answer does not exist anywhere in the document library as a single value. Instead, it exists as 12 individual rows in a spreadsheet with one entry for each month. To answer that question, the system does not need to find a document, it needs to perform a calculation across structured data. Standard retrieval, even the advanced vector kind, simply cannot do that. It returns chunks of text, but it does not run SQL and it does not add numbers together. The best vector search will just return the January row or the March row because those chunks happen to be semantically similar to the phrase total revenue. The model then tries to answer from a fragment, gets the math wrong, and the user stops trusting the system entirely. This is where agentic RAG separates itself from the basic approach. The agent in this system does not treat every question the same way. It has three distinct tools available: vector search for semantic questions, full document retrieval when it needs more context, and a SQL query tool for anything involving tables or math. When the question is total revenue in 2024, the agent does not guess. It writes a SQL query, runs it against the structured data table, and returns the exact number. The distinction matters because different types of questions require different types of retrieval. A system that only uses vector search will always fail on questions that need calculation, while a system that only uses SQL will fail on questions that need semantics. You need both, and more importantly, you need a system that is smart enough to decide which one to use. That is exactly what we are building. Now let's look at the full architecture before we get into the individual components. The full system architecture. We need to map out exactly what we are building before we touch a single configuration screen. The system lives in 5 layers. SharePoint sits at the top as the document source, and the Microsoft Graph API acts as the connector that bridges those files to our automation layer. n8n sits in the middle as the orchestrator, which is the brain that sequences every step and routes data between systems. Mistral OCR serves as the processor that converts raw documents into structured text, and at the bottom, Supabase running on Postgres acts as the memory. Sitting in front of all of this is OpenWebUI. It looks and behaves exactly like ChatGPT, but it is running on your own server and talking to your own private agent. Because it pulls from your own data, no third party ever sees the conversation and no data ever leaves your infrastructure. Within this architecture, there are 2 distinct pipelines that you need to keep separate in your mind. The first pipeline is ingestion. A file lands in SharePoint and the system detects it, downloads it, and processes it before storing a vectorized version in the database. This pipeline runs on a schedule every 5 minutes in this implementation, and it only focuses on files that are brand new or have been recently changed. The second pipeline is retrieval. When a user asks a question, that request travels from OpenWebUI to n8n through a webhook. n8n converts that question into a vector, searches the database, and then re-ranks the results before passing the relevant content to the language model. The model generates an answer and sends it back, and the user sees a response in just a few seconds. Those 2 pipelines share the same database, but they operate independently of one another. The ingestion pipeline is asynchronous and runs quietly in the background, while the retrieval pipeline is synchronous because it runs in real time. Understanding that separation is vital for performance because the only thing that affects the user's experience is retrieval latency, not the speed of ingestion. Everything in this stack runs in the European Union. That is a deliberate design constraint rather than a coincidence. n8n, Supabase, and OpenWebUI are all running on a VPS in Germany. The Azure OpenAI embedding model is deployed on Swedish servers, and the Mistral OCR model is hosted as a serverless instance in the Azure AI Foundry. Every component was chosen to ensure data sovereignty, and we will go into those compliance details later in the video. There's one practical point worth addressing right now. The entire stack can run on a single VPS, and a machine with 4 virtual CPUs and 4 GB of RAM can handle the whole thing. You do not need a massive cloud architecture on day one. A German VPS from Hetzner costs somewhere between 7 and 20 euros a month, which is a small price for a production-grade private AI system. As your workload grows and you add more documents or users, you can separate these components into dedicated containers. n8n can be split into a main instance and several worker instances, while Postgres and Redis can move into their own dedicated spaces. But that is a conversation about scaling, and it is not something you need to worry about when you are just starting out. There is one final structural point to remember. If you were planning to run this on n8n Cloud instead of self-hosting, you actually cannot. The agentic chunking step uses specific LangChain modules that are not available in the cloud version. Self-hosting is not just a preference for this implementation, it is a requirement built into the very architecture we are using. Now that we have the full picture in view, let's get into the first real engineering problem, which is connecting n8n to SharePoint in a way that actually works in a production environment. Connecting to SharePoint, the Graph API problem. n8n comes with a native SharePoint module that seems perfect at first glance. You drop it into your workflow, point it at your tenant, and within a few minutes you're pulling file lists from a document library. It looks like the problem is solved, but in reality it isn't. The SharePoint module has a structural flaw that stays hidden until you try to build something dynamic. When you use the getManyItems operation, the module returns a list of files with metadata like names, timestamps, and content types. But here's the problem. It doesn't return the actual file ID. It gives you the display name and the path, but it leaves out the real internal identifier that SharePoint uses to track a file when it gets renamed or moved. That might sound like a minor detail, but it's actually a deal breaker. Without that specific file ID, you cannot download a file dynamically. You can pick a file from a drop-down menu while you're setting things up, which hard-codes that choice into the node, but that doesn't help you in a live environment. The moment you want the workflow to download whichever file just changed, not a specific one you chose yesterday, but any file at runtime, the download step will break. This is exactly why most SharePoint tutorials fail when you actually try to use them. They show you how to connect to a single static file, but they don't show you how to build a system that responds to whatever happens in the folder. In a demo, these two approaches look the same, but in production, the difference is a system that works versus one that crashes the moment a user uploads a new document. To fix this, you have to run Microsoft Graph API calls alongside the SharePoint module. You aren't replacing the module. You're using both at the same time, because they each have something the other lacks. Graph API is the only way to get the real file ID. When you ask the Graph endpoint to list the contents of a folder, the response includes that internal identifier you need for dynamic downloads. The SharePoint module can't give you that, but Graph API can. However, Graph API has its own gap because it doesn't show the last modified timestamp as reliably as the SharePoint module does. You need that timestamp because the entire sync logic depends on it. The system has to know exactly when a file changed, so it can decide whether to process it again or just skip it. Because of this, the architecture uses two parallel paths at the start of the workflow. One path calls the Graph API to grab the file IDs, while the other path uses the SharePoint module to collect the last modified timestamps. Both paths look at the exact same folder and return a list of files. Then a merge node joins them together based on the file name. By matching the ID from the graph path to the timestamp from the SharePoint path, you end up with one complete record for every file. This is the core insight for the entire connection. You aren't just swapping tools, you're using both because each one produces a specific piece of data the other can't reach. These parallel paths aren't a workaround, they are the design. Before you start configuring anything, you have to plan for rate limiting. Graph API throttles your requests at both the tenant and the application level. Microsoft doesn't publish a specific ceiling for these limits, and their documentation says the rules change based on your workload and service conditions. In the real world, this means your system will hit HTTP 429 responses regularly, especially during the first big ingestion when you're processing a massive folder. When you get a 429 response, it includes a retry after header that tells you exactly how many seconds to wait. You must honor this number exactly. If you try again too fast, that failed attempt counts against your limit and makes the throttling even worse. You need to build exponential backoff into your workflow to read that header every single time. This isn't just a safety feature, it's a requirement for any application that talks to Graph API at scale. Once you understand that logic, the next step is setting up your credentials in Azure. Azure app registration step by step, start by opening the Azure portal and searching for app registration in the top bar. Using the search bar is the fastest way to get there since the feature is buried inside Microsoft Entra ID. Once the page loads, click New Registration to get started. You need to give the app a descriptive name so you'll know what it is 6 months from now. Something like n8n SharePoint RAG works well. For the supported account types, make sure you select Accounts in any organizational directory. Do not choose personal accounts or single tenant options, as this specific setting is what allows the app to work across your entire Microsoft 365 tenant. The redirect URL is where most people make their first mistake. You might feel tempted to type this in manually by adding a path to your n8n domain, but you shouldn't do that. Instead, open your n8n credential screen in a different tab and create a new OAuth 2 credential. Copy the exact redirect URL that n8n generates for you because that value is very specific. If you miss a single slash or a path segment, the OAuth handshake will fail silently. The registration will look like it worked, but the connection will never actually connect. After the app is created, head over to API permissions. This is where you define what the app can actually touch, and it's where most configuration errors happen. You are going to need 3 specific permission sets from Microsoft Graph. The first is OpenID permissions, specifically offline access, which is what keeps your connection alive. Without this, your access token will expire after a few hours and the workflow will just stop. It's a quiet failure where the system simply stops updating, and you won't notice until you see your database hasn't changed in days. Adding offline access allows the token to refresh automatically in the background. The second permission is Files, Read Write All. This gives the application the right to read and write files across the entire tenant. Even if you only plan on reading files for now, scoping this to read only often creates headaches later when you want to expand the system. It's better to start with read-write and tighten it later if your security team requires it. The third one is sites read-write all. You need this because reading SharePoint site contents requires site-level access, not just file-level access. If you skip this, your Graph API calls will return permission errors even if the individual file permissions look correct. Once those are set, you need to add one more permission specifically for SharePoint. Click Add Permission again. But this time, scroll past the Microsoft services and select SharePoint directly. Look under Delegated Permissions for My Files and add My Files. Right. This is a SharePoint layer permission that sits underneath the Graph layer, and you need both for the application to work. When the portal asks about the permission type, always choose Delegated Permissions instead of Application Permissions. Delegated permissions mean the app acts on behalf of the user who signs in, which is the account you'll use to connect n8n. Application permissions grant the app broad access without any user context, which usually requires an admin to sign off on it. Delegated permissions are the better choice here because they offer a narrower scope and a much clearer audit trail. Now, navigate to Certificates and Secrets and click the plus icon to create a new client secret. Give it a name and set the expiration to 730 days, which is the maximum allowed. When the secret is generated, the value will appear on your screen exactly once. You must copy it immediately and put it in a password manager or a secure note. Once you leave this page, the value is hidden forever, and if you lose it, you'll have to delete the secret and start over. Before you leave the Azure portal, go back to the app overview and copy the application ID. This is your client ID, and you'll need it along with the secret to set up your credentials in n8n. Now that you have both values, the Azure side of the setup is finished, configuring n8n credentials. When you get back into n8n, you need to set up two separate credential objects, not one, two. This distinction actually matters because the SharePoint module and the Graph API node use different ways to talk to Microsoft, even though they both lean on that same Azure app you just built. The first one is for the SharePoint module itself. If you open the setup screen for any SharePoint node, you'll see three specific fields: Client ID, Client Secret, and Subdomain. Your Client ID is just that application ID you grabbed from the Azure overview page, and the Client Secret is the value you generated under Certificates and Secrets. For the subdomain, just look at your SharePoint URL and take the part that comes before sharepoint.com if your site is Contoso. SharePoint.com, you just type Contoso and you're done. Once you save that and hit connect, a window will pop up asking you to sign in with your Microsoft account to make the connection official. The second credential handles the Microsoft Graph HTTP calls, which are the ones that actually go out and find your file IDs. This part is a little more hands-on. You'll need to create a new credential in n8n and select Microsoft OAuth 2 API as the type. You are going to use the exact same client ID and secret from before, but this time there is an extra field that the standard SharePoint module doesn't show you, the permission scopes. This field needs a long string of permissions separated by spaces, and you have to type them out perfectly. You need to enter files, read-write.all sites, read-write, all offline access open ID. The order of these words doesn't change anything, but the spacing is vital. You have to use a single space between each one with no commas or extra lines, or the whole thing breaks. When you try to connect, Microsoft checks this list against what you authorized in Azure. If there is a typo or a mismatch, the system will either refuse to give you a token or give you one that doesn't actually have the power to do anything. I want to pause on that offline access scope for a second, because it is the one thing almost everyone forgets. When you leave that out, the failure is incredibly annoying to track down. Without it, Microsoft gives you a token that only lasts about an hour. Everything looks great during your initial test, but then you walk away and come back a few hours later to find every workflow failing. You'll check the logs and see 401 unauthorized errors even though you didn't change a single setting. The connection will even look green in n8n, but the token is dead, and without that offline scope, n8n has no way to refresh it automatically. By adding offline access to that string, the server sends over a refresh token along with your main access key. This allows n8n to go out and grab a fresh key before the old one dies, which keeps the connection alive forever without you ever having to log in again. That is exactly what you want for a background process that is supposed to run every 5 minutes. After you have both of these saved and green, you need to test them individually. Run the Graph node by itself to make sure it pulls data from the site, and then run the SharePoint node to see if it can see the files in your folder. You need to be 100% sure both sides are working on their own before you try to merge them together. One last thing on the maintenance side, your client secret is going to expire in 730 days. Do yourself a favor and put a reminder on your calendar for day 700. If that secret expires, every single workflow you have tied to SharePoint will stop working at the exact same time. Updating it only takes about 10 minutes since you just generate a new secret in Azure and paste it into n8n, but you want to do that before the clock runs out. If you wait until it breaks, you'll be stuck cleaning up a massive backlog of files that didn't sync while the system was down. Now that the credentials are live, n8n can finally talk to both SharePoint and the Graph API. The plumbing is finished, so now we have to figure out the logic for which files actually need to be moved. The file sync logic. Every 5 minutes, this ingestion workflow kicks into gear. The problem is that it has no idea what happened in SharePoint while it was asleep. It doesn't know if you added 10 files or deleted 20, and its first task is to figure that out without having to reprocess every single document from scratch. Efficiency is the big goal here. If you have a library with hundreds of files and you're running them through OCR and AI chunking every 5 minutes, you are going to burn through a massive amount of time and money. Instead of doing all that work over and over, the system asks one very specific question. What has changed since the last time I looked? To track this, we keep a simple metadata table in Postgres with 3 columns for the file ID, the file name, and the last modified timestamp. This table is basically the system's memory of what SharePoint looked like the last time the workflow finished. When the workflow starts, it pulls the current state of the folder by combining the file IDs from Graph with the timestamps from SharePoint. Then it pulls that list from your Postgres table. Now the system is holding 2 different lists, what is actually in SharePoint right now and what the database remembers from 5 minutes ago. We use a code node to compare them. That comparison creates 3 possible scenarios, and the system handles each one differently. The first scenario is when a file ID shows up in SharePoint but isn't in your database. This is obviously a new file. The system creates a new row in the metadata table and then sends that file through the whole pipeline to be downloaded, chopped up, and turned into vectors. The second scenario is when the file ID exists in both places, but the timestamp in SharePoint is newer than the one in your database. This means the file was edited. When this happens, the system has to do some cleanup first. It goes into your vector database and deletes every single chunk associated with that file ID, so the old information is gone. If it was a spreadsheet, it clears those rows out too. Once the old data is wiped, it reprocesses the file from scratch and updates the timestamp in the metadata table to match the new version. The third scenario is when a file ID is in your database but is missing from SharePoint. This means the file was deleted. The system responds by scrubbing that file's data from the entire system, including the vectors and the metadata entry. This is how you handle the right to be forgotten automatically, because the moment a file vanishes from the source, it vanishes from your AI's memory too. If the code node looks at the lists and realizes nothing has changed, it simply stops. It won't output anything, which means no extra processing, no database writes, and no clutter in your logs. It just waits for the next 5-minute cycle to start. There is one tiny detail in the merge step that can absolutely wreck this logic if you aren't careful. The SharePoint module usually gives you clean file names, but the Graph API sometimes sends them back with URL encoding, where a space looks like %20. If you try to join these 2 lists based on the name and one says project plan, while the other says project 20 plan, the join will fail. The system will think the old file was deleted and a new one was created, leading to a loop where it reprocesses the same files over and over. You can fix this easily by putting a small decode step right after the Graph API call. You just need a tiny bit of code to turn those % signs back into normal characters before the data hits the merge node. It's a small fix, but it prevents ghost entries from filling up your database and breaking your sync. Once the sync logic is giving you a clean list of files that actually need work, you're ready to start the download. But as soon as that file hits the system, you have to decide exactly where to send it based on what kind of file it is. Downloading and routing files. Downloading the file is a simple step once you have that file ID. You send a single request to the Graph API, pull the ID from your record, and the API hands back the file as binary data. This is why we built that parallel path architecture earlier. The ID you got from the Graph API is the only key that opens this door. Without it, the process stops. With it, the download happens in one single node. But what happens right after the download is where the logic actually gets interesting. You can't treat every file the same way if you want the system to be useful. The moment that binary data hits n8n, the workflow looks at the file extension and splits the path. Excel and CSV files go to one side. Everything else, like PDFs, Word docs, and text files, goes to the other. This split exists because of how the agent needs to find information later. Tabular data and prose have completely different requirements for retrieval. Usually prose gets vectorized. You break it into chunks, turn those into embeddings, and save them in a vector table. This works great for questions like, how does the espresso machine work? Because the meaning of the question matches the meaning of the text chunk. But spreadsheets don't work like that. A row in a budget sheet showing revenue for March doesn't have meaning in a way a vector search can understand. It just has a value and a structure. If you vectorize a row that says March 18500, the embedding has almost no useful signal for a question about yearly totals. A vector search will just grab whatever row looks similar to the words in the question. It might give you March or it might give you October, but it definitely won't give you the sum of the whole year. Because of this, Excel and CSV files skip the vector pipeline entirely. Each row gets written as an individual record into a Postgres table called document rows. We store the data as JSON right next to the file ID and the original file name. The structure stays exactly how it looked in the spreadsheet. We don't summarize it, we don't chunk it, and we don't embed it. This makes the table something the agent can actually query using SQL. When a user asks a question that needs math or needs to look across multiple rows, the agent writes a query against that table instead of searching the vector store. The database handles the calculation and the agent just reports the answer. This routing decision is the reason the system can answer two totally different types of questions. If you vectorize everything, you fail at math. If you only store structured rows, you fail at general knowledge. By branching the workflow here, you avoid both of those traps. In a typical company library, most files will take that second path. Your PDFs, manuals, and contracts all head toward Mistral OCR, which is where the real work of pulling out information begins. Why Mistral OCR? Most people start by using the built-in extract from file node in n8n. You drop it in, point it at your data, and it pulls out the text. If you have a clean PDF that was created digitally with a simple layout, it works fine. But most files in a SharePoint library aren't clean. They are scanned manuals, invoices with weird tables, or contracts with complex layouts, and that's where the standard tools fail. These failures are dangerous because they are hard to see. The standard extraction node can't see images at all. If a PDF has a diagram or a scanned page, that content just vanishes from the output. There is no error message, and the node says it succeeded. It just returns whatever text it found and moves on. Your vector database ends up with a broken version of the file, and your agent starts answering questions based on missing information. Since nothing logged an error, you'll never know why the answers are wrong. Complex layouts make things even worse for standard nodes. Multi-column text or tables with merged cells usually break the extraction logic and turn the document into a mess. A table that should be structured rows comes back as a random string of numbers in the wrong order. The agentic chunker can't do its job because the material it receives is already corrupted. Mistral OCR handles this differently because it doesn't just try to parse a file format. It actually looks at the document. It treats every page like an image and identifies where the text is, where the tables are, and what the reading order should be. Then it rebuilds everything as structured markdown. It isn't just parsing a file, it's actually understanding a layout. The numbers show how much of a difference this makes. In tests across 1,000 different documents, Mistral OCR hit nearly 99% accuracy on scans and over 96% on tables. Even with handwriting, it stayed around 89%. Compare that to Azure or Google, which usually land between 83 and 90% on the same files. Those gaps might seem small, but they add up fast. A 10% difference across 500 files means 50 of your documents are feeding bad data into your system. The output format is another reason we use it. Mistral doesn't give you a wall of plain text. It gives you markdown, which means headings stay as headings and tables stay as tables. This structure is exactly what the agentic chunker needs to decide where to split a document. Splitting at a heading is a smart move, but splitting in the middle of a table ruins the data. The quality of your chunks depends entirely on the quality of the text that arrives at that step. Then you have the way it handles images. When Mistral finds a picture, it leaves a description and a placeholder right there in the markdown. Our pipeline takes those descriptions, moves the original images to storage, and swaps the placeholders for real URLs. The document moves through the rest of the system with the images exactly where they belong. On the cost side, it's about $2 for every 1,000 pages or $1 if you use batch mode. For a library that only changes once in a while, that cost is basically nothing. Since Mistral OCR runs inside Azure AI Foundry, it stays compliant with GDPR. You can run it on EU-hosted servers under the same rules as your other models, keeping your data residency exactly where it needs to be. Agentic chunking, why it matters. Mistral OCR delivers a markdown document that is clean, structured, and complete. It gives you the text, the image references, and the heading hierarchy. But there is a major problem, the sheer size of the file. A 10-page product manual might hit 4,000 words, while a 30-page policy document can easily reach 12,000. You cannot simply drop 12,000 words into a vector database as a single block and expect the system to find anything useful. Every embedding model has a context limit. Even if you stay within that limit, a single vector representing 12,000 words of mixed content carries almost no specific signal. The similarity search becomes nearly useless at that scale. If a user asks about safety requirements for an electrical panel, the system will technically find the document about electrical panels, but it will match every single chunk of that document equally, because the vector for the whole file is just an average of everything inside it. That is why we split documents into chunks. This isn't a design choice. It is a hard requirement for how vector search actually works. The real question is how you decide where to cut, because that choice determines the quality of every answer the system gives. The naive approach is to cut at a fixed character count. You tell the system to make a cut every 1,000 characters. It is simple to set up and costs nothing in terms of compute, but the results are consistently bad. It cuts in the middle of a sentence. It breaks a table in half. It separates a numbered step from the instruction it was supposed to explain. When you separate a heading from the content beneath it, the chunk that lands in the vector store is missing its context. When that fragment is retrieved later, the language model receives a piece of information that only partially makes sense. The answer it generates will always reflect that incompleteness. The 2,500 token boundary is the number that actually matters here. Research shows that response accuracy starts to drop once individual chunks exceed roughly 2,500 tokens. Below that limit, the model can hold the entire chunk in focus and reason across the details. Above it, the model's attention starts to diffuse. It isn't a total failure, but it is enough to degrade the quality of your answers at scale. The goal is to keep complete thoughts together while staying below the size where the model starts losing the thread. Agentic chunking solves this by using a language model to decide where the cuts should happen. Instead of a blind character count, the full text goes to a model, in this case a GPT series model on Azure OpenAI. We give it a specific prompt to find the logical boundaries. We tell it to keep arguments together, keep numbered lists intact, and never separate a heading from its section. The model reads the document and identifies exactly where the topics shift or where a new idea begins. It returns a segmented version where every chunk starts and ends at a point that makes semantic sense. An installation procedure stays as one unit. A paragraph about pricing exceptions doesn't get split across two chunks, which prevents the context from being on one side and the actual price on the other. This process does come with a cost. Every document you process requires one additional LLM call for a document library that updates slowly, which is the case for most corporate SharePoint sites. That cost is easily absorbed during the ingestion cycle. The system isn't under pressure to perform in real time here. It processes files as they change, so a document updated once a month only triggers one agentic chunking call once a month. The math changes if you have high-frequency ingestion. If you have thousands of new files arriving every hour from automated processes, agentic chunking creates a bottleneck and a bill that probably isn't worth it. In that specific scenario, recursive character splitting with semantic overlap is the better move. But for a standard corporate knowledge base, agentic chunking should be your default. The improvement in retrieval quality compounds over time, and you only pay that ingestion cost once per update. Once the chunks are sized correctly and cut at logical boundaries, they are almost ready for the vector database. But before they go in, we have to handle the images. Image processing and storage. Mistral OCR doesn't just ignore images when it sees them, it annotates them. It places an inline reference in the markdown output, a placeholder that marks exactly where the image was in the original file, along with a description of what it shows. That annotation stays with the text as it moves through the pipeline. But a placeholder is just text. If you want the agent to actually show an image to a user, those placeholders have to become real URLs pointing to real files. That is the job of the image processing step. Once the OCR is done, the pipeline scans the text for those image annotations. When it finds one, it pulls the corresponding image data, which Mistral provides in its response, and uploads it to a Supabase storage bucket. Supabase gives us a storage layer on top of Postgres specifically for these kinds of files. Each image gets a public URL, and that URL replaces the placeholder in the markdown. By the time the document reaches the chunking and embedding stage, the image references have already been turned into live links. The word public is very important here. For the agent to show an image in a chat and for the UI to render it properly, the URL must be accessible without a login. OpenWebUI doesn't have the credentials for your Supabase bucket. It just tries to display whatever the agent sends back. If that image URL requires a signed token or a session cookie, the process fails silently, and the user just sees a gap in the answer. We configure the bucket for public read access, which means these images are not secret. Anyone who has the URL can see them. This brings up a major GDPR caveat. If your documents contain images with personal data, like photos of people, signatures on contracts, or scans of ID cards, a public bucket is a mistake. You would need to change the model. Either the bucket stays private and the agent generates short-lived links at the moment of the response, or you filter those images out entirely. The default setup assumes your images are technical diagrams or equipment photos. If your SharePoint library has sensitive personal info, you need to check your bucket policy before going live. When this works correctly, the experience is completely different from standard search. A user asks how to fix a machine, and the agent gives a structured answer. Step 1, Step 2, Step 3. And right next to the text, the actual image from the manual appears in the chat. It isn't a link or an attachment. It is an inline image exactly where it belongs. That happens because Mistral captured the position, the pipeline preserved it through the chunks, and the system prompt told the agent to put the images exactly where they appeared in the original document. Now that the text and images are resolved, the final step is turning those chunks into vectors. Vectorization and the embedding model. A chunk of text is still just text, and your vector database cannot search it directly. Before anything lands in storage, that text has to be converted into a form that allows for mathematical comparison. This takes the form of a list of numbers, usually ranging from several hundred to over 1,000, where every digit captures a specific aspect of what the text actually means. That list is what we call a vector. When two chunks discuss similar concepts, they produce vectors that sit close together in that numerical space, while unrelated topics produce vectors that sit far apart. Similarity search is just the process of finding which stored vectors are closest to the one generated from a user's question. The model that handles this conversion is the embedding model. It takes text in and returns a vector out, and it does this with total consistency, so the same input always produces the same output. That reliability is exactly what makes retrieval work. If a user asks how to operate the espresso machine and a document chunk says to press the button on the left to start the heating cycle, those two strings don't share many words. But because they describe related things, their vectors end up as neighbors in the embedding space, and the similarity search surfaces that chunk as relevant. In this stack, the embedding model runs through Azure OpenAI using a text embedding model deployed under the EU Data Zone standard configuration. This specific deployment choice is a critical detail. Azure OpenAI offers two ways to deploy these models, which are Global Standard and Data Zone Standard. Global Standard routes your requests to whichever Azure region has open capacity at that moment, which means your text and your organizational knowledge might be processed on servers outside the EU. Data Zone Standard is different because it constrains all processing to Azure regions inside EU member states. For this system, that setting is non-negotiable. The documents being embedded contain internal business information, and letting that content leave EU jurisdiction during the embedding step would create a transfer risk that breaks the entire GDPR architecture. The Swedish Azure region hosts the deployment for this project. Microsoft's EU data boundary commitments apply here, so the embedding calls go in and the vectors come back without any part of that exchange crossing outside European infrastructure. Those vectors eventually land in a Postgres table inside SuperBuzzy. The table uses a vector column powered by the pgvector extension, which is a Postgres add-on that adds a native vector data type and support for similarity queries. The index type used here is HNSW, or Hierarchical Navigable Small World. It is an approximate nearest neighbor algorithm that trades a tiny bit of precision for significantly faster query times when compared to an exact search. For retrieval at conversational speed, that is the right trade-off to make. A user waiting for an answer in a chat interface does not care about the microsecond precision improvement of an exact search, but they definitely benefit from a response that arrives fast enough to feel like a real conversation. Performance at this scale is not a major concern. A corporate SharePoint library rarely produces more than a few million chunks, even if it is quite large, and pgvector handles that volume on modest hardware without slowing down. If the system ever grows into a multi-tenant deployment or starts ingesting libraries from across an entire global organization, the Superbase vector buckets architecture is a path that can handle tens of millions of vectors. For a single-tenant enterprise rack system, the standard pgvector table is the best starting point. Each row in that table stores more than just the embedding. It keeps the file ID, the original file name, and the chunk index, which tells the system exactly where that piece of text sat within the original document. This metadata is what allows the agent to tell a user where the answer came from, instead of just what the answer is. Every response is traceable back to a specific section of a specific file, which is vital for building user trust and maintaining GDPR accountability. The answer is never a black box, because the source is always visible. How the agent retrieves information. The ingestion pipeline is finished. The documents are processed, chunked, embedded, and stored, so now the system just needs to answer a question. When a user opens the interface and types a message, that text travels from the browser to n8n through a webhook. This is a simple HTTP post that carries the question and a session identifier to link the message to the conversation history. Once n8n receives the data, the retrieval pipeline starts moving. The first step is a mirror of what happened during ingestion. The question text goes to the same Azure OpenAI embedding model that processed the document chunks, and the model returns a vector representing the meaning of that question. That vector is then compared against every single vector stored in the Superbase table. The database calculates a similarity score between the question and each stored chunk, sorts them by that score, and returns the top results. The system is set up to return 25 candidates from that initial search. 25 sounds like a lot, and in reality it is. If you pass all 25 chunks directly to the language model, you create a new problem because the model's attention gets spread across too much material. Answers start to become vague as the model blends details from multiple chunks rather than grounding itself in the most relevant one. The constraint here isn't the size of the context window, but rather the quality of the model's attention. A model given 25 chunks of moderately relevant content almost always performs worse than a model given 4 chunks of highly relevant content. This is where re-ranking enters the pipeline. Cohere Re-rank v3.5 takes those 25 candidates and scores each one specifically against the user's question. This is a different process than the first search. Vector similarity measures how close two pieces of text are in a mathematical meaning space, which is a geometric relationship. Re-ranking is a relevance judgment that measures how well a specific chunk actually answers a specific question. While those two things usually correlate, they are not the same thing. A chunk might be semantically related to a question without being useful for answering it, and re-ranking is what catches that difference. The re-ranker produces a new ordering of those 25 chunks based on how well they support the specific question asked. The system takes the top 4 from that new list and discards the rest. 4 chunks go to the agent while 21 chunks get dropped, and that filtering step is what keeps the agent's context tight and its answers specific. The number 4 is not a random choice. During testing, 4 chunks represented the sweet spot where the context is rich enough to answer multi-part questions without becoming so diluted that the responses lose focus. If you use fewer than 4, you run into gaps when a question requires information from different sections of a document. If you use more than 4, the precision starts to drop. While the right number can shift depending on how dense your documents are, 4 is the correct default for a corporate knowledge base built from typical enterprise files. There is one part of this pipeline that requires a GDPR note, and that is the Cohere re-ranking call. Cohere is a Canadian company, and the EU has formally recognized Canada as a country that provides adequate data protection under GDPR Article 45. This means that data transfers to Canadian processors do not require extra safeguards like standard contractual clauses. The question text and the 25 candidate chunks pass through Cohere's model, and that transfer is compliant as it stands. If you work in a sector like financial services or healthcare, where any data leaving EU infrastructure triggers a manual review, you should verify this against your specific legal requirements. For most enterprise use cases, the adequacy determination covers the transfer. The 4 re-ranked chunks and the original question finally go to the agent as context. The agent's job at this stage is not retrieval because the retrieval is already done. Its job is generation, which means reading the question, looking at the provided chunks, and producing a coherent answer grounded in that content. But before it writes a single word, it checks whether the retrieval path was actually the right tool for the job, because sometimes it isn't. The 3 agent tools. The agent has 3 tools at its disposal. Understanding when it uses each one and why that decision happens at the agent level rather than being hard-coded into the workflow is what separates this architecture from a basic chatbot. Tool 1 is vector store retrieval. This is the default path for the system. When a question comes in and the re-ranked chunks cover the right information, the agent reads those snippets and generates an answer. Most questions in a corporate knowledge base land right here. You might ask about the return policy for enterprise customers, or which safety protocol applies to a specific facility, or what a service agreement says about response times. These are semantic questions about pros, and the vector pipeline handles them perfectly. Tool 2 exists because vector retrieval isn't always enough. Imagine the agent gets a question about a specific product specification. The re-ranked chunks return a few relevant sections, but the agent can tell from those fragments that the full answer requires reading the entire document. It sees that the chunks are just pieces of a larger argument that only makes sense in sequence. In that case, the agent calls Tool 2 for full document retrieval. It takes the file ID from those chunks, queries the vector table for every piece belonging to that document, and reconstructs the full content in the correct order. This is more expensive than returning 4 small chunks, but it's the right move when those chunks aren't sufficient. The agent makes that judgment call so you don't have to guess which documents will need a full read. Tool 3 handles a class of questions that neither of the first 2 tools can answer. Anything involving arithmetic, filtering, or comparing data across tables goes here. Instead of searching for text, the agent queries the document rows table directly using SQL that it writes itself. That last part is important, so let's look at it closely. The agent doesn't get a pre-written SQL query, and it doesn't use a template with empty slots for column names. It reads the question, figures out what data operation is needed, and writes the query from scratch. When a user asks for total salary expenses in the 3rd quarter, the agent determines this requires summing a column and filtering by a date range. It writes the select statement, the database executes it, and the agent returns the final result. Why let the agent write SQL instead of doing the math itself? Because language models are structurally unreliable at arithmetic. It isn't an occasional glitch. The way a model processes numbers is fundamentally different from how it handles language. It predicts tokens. For text, token prediction works because language has patterns the model understands. For math, token prediction produces outputs that look like numbers but aren't always right. The error rate on multi-step calculations is a real problem even for the best models. SQL has no such limitation. The database calculates the answer exactly every single time, regardless of how many rows it has to count. Using SQL isn't a workaround for a weak model, it's just using the right tool for the job. The system prompt connects these 3 tools into one framework. It tells the agent the sequence to follow. Start with RAG. If the vector results don't have a clear answer, check the metadata, find the right file, and pull the whole thing. If the question involves a calculation, skip the vector path and go straight to SQL. There is one more instruction every deployment needs. When none of the tools return enough information to answer the question, the agent must say so. It shouldn't synthesize an answer from nearby content or fill gaps with details that sound plausible. It needs to respond with a clear statement that the answer isn't in the documents. This ability to decline is what makes the system trustworthy. A system that always gives an answer is a system that eventually gives a wrong answer with total confidence. That is a much harder failure to catch than a system that simply admits it doesn't know. Writing the system prompt. The system prompt is where the architecture actually becomes a behavior. Everything we've built so far, the tools, the pipeline, and the image handling, exists only as a capability. The prompt is what turns that capability into reliable action. Without it, the agent has the right tools but no way to choose between them. If the prompt is weak, the agent defaults to what it knows best, which is treating every single problem like a vector search. Think of the system prompt as the contract between you and the agent. It defines the terms of engagement by telling the agent what it knows, what it should do in specific situations, and what it must never do. Every messy case the agent hits in production is something the prompt either handled or it didn't. The ones it missed become the edge cases you only discover when the system fails. 4 core instructions make this architecture work. The first is to always start with RAG. The vector store is the default path, and the agent should reach for it first, no matter how the user phrases the question. This prevents the agent from jumping to full document reads for every query. Those full reads are expensive and slow, so they should only happen when the initial search fails to provide enough context. The second instruction covers escalation. If RAG returns insufficient context, the agent must consult the metadata and retrieve the full content of the most relevant file. This path is for questions that are document-specific rather than fragment-specific. You have to be explicit here because agents don't escalate on their own. They usually try to answer with whatever they have, even if it's incomplete. Telling the agent to recognize when it's missing information is the only way to make this reliable. The third instruction is about the math. If the question requires any calculation or cross-row comparison, the agent must use the SQL tool. It should never attempt arithmetic through the language model itself. This needs to be a direct command. Saying use SQL for numerical questions is much better than prefer database operations where appropriate. Vague instructions lead to inconsistent results. The fourth instruction is one most people miss. When images appear in the retrieve chunks, the agent should render them inline exactly where they appear in the document. It shouldn't collect them all at the end of the response. This matters more than you might think. The default behavior for a model is to finish the text first and then list the media at the bottom. That disconnects the image from the step it's supposed to illustrate. Putting the image where it belongs makes the response feel like a real manual instead of a text file with attachments. 2 more instructions finish the prompt. Tell the agent to always cite the source file name when it uses document content. Then, tell it to be honest when it doesn't know the answer. No making things up, no guessing, and no pulling from unrelated files just to fill the space. If you leave those out, the agent starts blending content from different documents without telling you where it came from. It starts building answers that sound right, but are actually wrong. Both of these behaviors kill trust fast. Once your users stop trusting the system, they'll stop using it entirely. The system prompt isn't something you write once and forget. Every time the agent misroutes a question or fails a calculation, that's feedback that your instructions need to be sharper. Treat the prompt as a living document that grows alongside the rest of your workflow. Self-hosting, infrastructure decisions. Where your system runs determines what it can actually do. This isn't just a technical detail, it's a constraint that eliminates certain choices before you even make them. It starts with agentic chunking. This is the method that uses a language model to find logical split points in a document, and it requires LangChain modules inside n8n to work. But here's the problem. Those modules are only available on self-hosted n8n instances. They don't exist on n8n Cloud. If you want intelligent chunking to improve your retrieval quality, self-hosting isn't just a preference, it's a prerequisite. The cloud version of n8n simply cannot run this workflow. That constraint also answers the cost question for you. The standard n8n Cloud plan costs about €24 per month and puts a cap on how many times your workflows can run. A system that polls SharePoint every 5 minutes generates 288 cycles every single day before you even process a document. Once you add ingestion workflows, retrieval webhooks, and deletion checks, you'll burn through a monthly execution budget within the first week. Self-hosted n8n has no execution ceiling because you pay for the compute power, not for the number of times a workflow runs. To get this system off the ground, you only need a single virtual private server with 4 vCPUs and 4 GB of RAM. You can run n8n, Supabase, and OpenWebUI in Docker containers on that same machine without any issues for development work or light document libraries. But for production, that single machine setup is too fragile. One heavy ingestion workflow, like a large PDF hitting Mistral OCR and then moving to agentic chunking, can hog enough resources that your retrieval webhooks start timing out. Users will experience delays when they ask questions because the background pipeline is fighting for the same CPU. The production architecture fixes this by separating those concerns. You run n8n in queue mode, which splits the application into 2 different processes. You have a main instance that handles the user interface and triggers, and then you have worker instances that actually do the heavy lifting by pulling jobs from a Redis queue. When a new document arrives, the main instance puts the job on the queue and stays responsive for user requests while a worker processes the file in the background. This way, the 2 workloads stop competing for the same resources. Redis is a lightweight addition that needs almost no resources at this scale, but you should run Postgres as its own separate container. Separating the database is important because Postgres can spike disk usage during large ingestion batches, and that can slow down everything else on the machine if they're sharing the same storage. Your hosting location is a GDPR requirement, just as much as an infrastructure choice. Using a provider in Germany like Hetzner puts your entire stack inside EU jurisdiction with zero ambiguity. There is no Cloud Act exposure for the data sitting in Postgres and no risk for the vectors stored in Superbase. You won't have to worry about where your execution logs live, because the data boundary is the server boundary. That simplicity makes things much easier when you have to complete a data protection impact assessment and describe exactly where the data goes. A production-grade setup with a main instance, 2 workers, dedicated Postgres, Redis, and OpenWeb UI usually costs between 15 and 25 euros per month. That covers your full stack. When you compare that to n8n Cloud alone at 24 euros, which has execution limits and no LangChain support, the choice is clear. Self-hosting costs less and removes every single constraint the cloud version would put on you. The only real trade-off is that you have to keep n8n updated yourself. The Docker Compose update process is just 3 commands to pull the new image and restart the containers, which usually takes under 2 minutes. You should schedule this once a month. If you fall too many versions behind, you'll run into compatibility gaps between your workflow nodes and the runtime, and those usually show up as silent failures rather than obvious errors. GDPR architecture, what actually matters. Most teams treat GDPR compliance like a checklist they can finish after the system is already built. They wait until legal asks for documentation to start thinking about it. That approach leads to systems where the architecture is technically sound, but the compliance is just bolted on as an afterthought. You end up with access controls that don't fit the design and data residency claims that fall apart the moment someone actually traces a request through the stack. The system we're talking about today was built the other way around. Compliance constraints shaped every architectural decision from day one. This isn't about being philosophical, it's just practical. Retrofitting a system is much harder than designing it correctly the first time, and the mistakes people make when they try to fix things later are usually the ones that lead to breach notifications. There are 3 specific data flows in this system that carry GDPR risk. The first is document ingestion. Every time a document moves from SharePoint through the OCR pipeline and into the vector store, it might contain names, contact info, or employee records. Each step in that process is a potential exposure point if your infrastructure isn't set up right. In this stack, every one of those steps runs on EU infrastructure that you control. The call to the Graph API goes to Microsoft, which you can't avoid, but everything after that happens on hardware you manage in a jurisdiction you chose. The second flow is the embedding step, and there is a very specific pitfall here. Azure OpenAI offers different deployment types, and if you use global standard, your requests are routed to whichever region has space. During busy times, your EU text could be processed on servers in the United States, which is a data transfer that's very hard to justify under GDPR Article 44. Using data zone standard solves this completely because the processing stays within EU member states regardless of the load. It's a single setting in your Azure deployment, but the compliance difference is massive. The third flow is your vector database sovereignty, and this is where your choice of vendor really matters. In a 2026 analysis of vector database providers, Pinecone scored 19 out of 25 for Cloud Act exposure because they are headquartered in San Francisco. This means US agencies can compel them to hand over data regardless of where that data is physically stored. Hosting in the EU doesn't change the corporate structure. However, running PG Vector on a German VPS or using QDRANT in Berlin gives you a score of 0. The vectors in your system represent the core knowledge of your company, so where that data lives legally is just as important as where the server sits. Beyond the main data flows, there are 3 operational areas that most people ignore. Your n8n execution logs record exactly what ran and what the inputs were, which means those logs can become a hidden archive of personal data. Postgres query logs have the same issue at the database level, and OpenWeb stores your entire conversation history. Every question a user asks and every answer the system gives is sitting in a table somewhere, and you have to be able to find it if a deletion request comes in. None of these things are inherently against the rules. They only become problems when you don't have a retention policy or a clear path to delete the data. You need to design your deletion path from the very beginning. When a document is removed from SharePoint, your sync logic should delete the vectors and the metadata, but it also needs to clear out any cached responses or conversation history that used that document. The right to erasure under Article 17 doesn't stop at the database. It follows the data wherever it goes. Every table you build should have a clear path back to the original file ID. When that ID is deleted, everything connected to it should disappear automatically, which makes handling erasure requests much easier than doing it manually. Failure modes and how to handle them. Every production system breaks in ways your development environment never predicted, and this setup is no different. But the failures that actually matter aren't the obvious ones. You won't always see a credential that won't connect, a node throwing a bright red error, or a workflow that just stops. Those are easy to fix because you can see them. The dangerous failures are the ones that look like a total success. The workflow finishes, the execution log shows green. But somewhere downstream, a document is missing from your vector store, a calculation is wrong, or a chunk boundary landed right in the middle of a table that should have stayed in one piece. Graph API throttling is the most predictable way this stack fails, which makes it the easiest to plan for but the most expensive to ignore. Microsoft doesn't give you a fixed ceiling for these calls. Instead, the threshold shifts based on your tenant activity and the current load on their services. You can be certain that your system will hit this limit eventually. A background job that polls SharePoint every 5 minutes to download files will generate enough volume to trigger a 429 error within hours of a big update. When you see that 429 response, you need to read the retry after header and wait exactly as long as Microsoft tells you to. Don't try again immediately or after a random 2-second pause. If you ignore that header and retry on your own schedule, every attempt counts against your budget, which just makes the outage last longer. Silent OCR failures are even harder to catch because the system doesn't announce them. Mistral OCR might return an empty response or malformed markdown if a document is too complex or the file size is too large. In a pipeline without validation, the workflow just accepts that empty response as valid and passes it to the chunking step, which results in nothing being written to your vector store. The file gets marked as processed in your metadata table, but later on, when an agent queries the store, it finds a massive gap where information should be. You can fix this by placing a validation node right after the OCR call. Check for a minimum content length and make sure the markdown structure is actually there. If the check fails, log the error and queue the file for a retry instead of pretending the job is done. Stale vectors are a much subtler problem to solve. Your sync logic usually depends on the last modified timestamp changing when a document gets updated, and most of the time that works fine. However, some SharePoint desktop clients don't always update that server-side timestamp the way you'd expect when they upload a modified file. A file gets changed and uploaded, but the timestamp stays the same or only moves by a fraction of a second, so it falls right outside your detection window. The vector store keeps the old version. To catch this, you need a content hash check as a fallback. If you hash the downloaded file and compare it to the stored hash from the last time you ingested it, a mismatch will trigger a reprocess even if the timestamp didn't. The merge step has its own specific failure pattern where Graph API results and SharePoint results join up based on the file name. SharePoint likes to encode special characters in file names as URL strings. This means a file named Q3 report and summary PDF might show up from one source as a plain string and from the other as Q3%20 report %20% to 6%20 summary PDF. The merge node compares those two names, decides they don't match, and simply drops the file from the process. Nothing gets handled and nothing gets logged. You need to decode those URL file names in both paths before they ever reach the merge node. Monitoring this whole system requires you to go way beyond the basic execution logs in n8n. Those logs only confirm that a workflow ran, but they don't tell you what that workflow actually produced. You should add explicit logging nodes after the OCR step, after the vector write, and after every SQL operation. Log your document IDs and chunk counts to a dedicated table. When something eventually goes sideways, that table is exactly where your investigation needs to start. The user experience. OpenWebUI looks almost exactly like ChatGPT. That choice is intentional, and it matters a lot more than you might think. Every single interface decision that requires you to train your users is just another barrier to them actually using the tool. If your team has to read documentation or sit through a walkthrough before they can ask a simple question, you're starting with a deficit. OpenWebUI gets rid of that friction because the interface is just a chat window. Everyone already knows how a chat window works. From the perspective of a user, the whole experience is very straightforward. They type a question and the agent starts thinking. You can actually see the tool calls happening if you have that view turned on, and you'll watch the system work through retrieval and re-ranking in order. For most questions asked against a standard corporate library, you'll get an answer in well under 10 seconds. If you're running complex SQL queries against huge datasets, it might take a little longer because the database work adds an extra step. Even then, the latency feels conversational. It feels like a chat, not like waiting for a report to generate. Images show up exactly where they belong in the flow. They aren't stuck at the bottom of the screen as thumbnails, and they aren't icons that you have to click to open. They appear in line and in the right sequence, appearing at the exact spot they occupied in the original document. If the answer to a question is that step 3 requires pressing the valve on the left, the image of that valve will be right below that sentence. The response feels like reading a page from the original manual rather than a text file that lost its pictures along the way. Every answer the system gives includes a source citation. The file name appears right next to the content it pulled from, so users can verify the answer against the original document in SharePoint. This traceability completely changes how people relate to the system. You aren't asking them to trust an output they can't verify. Instead, you're giving them a clear starting point to check the facts for themselves. That distinction is what makes enterprise adoption possible, because most companies won't touch an AI tool that gives answers they can't track back to a source. When the system doesn't have the answer, it tells you that directly. There is no hedged language that sounds like a partial answer, and it won't try to stitch together unrelated content to sound confident. It just gives a clear statement that the info isn't in the documents. Users learn very quickly what the system can and can't do, and that honesty makes the successful interactions feel much more reliable. Your conversation history stays put across different sessions. If you return to a chat thread a week later, the context is still there and the agent remembers what you discussed. It knows which documents you referenced and what follow-up questions you already asked. This continuity makes long-term research practical because you can build your understanding over several days instead of starting from scratch every time you log in. The interface itself isn't something you're locked into forever. OpenWebUI is the default because it's polished and you can host it yourself, but any front end that uses a webhook will work. Whether it's a custom internal portal, a Teams integration, or a simple form on your intranet, everything connects to the same n8n retrieval pipeline without you needing to change the underlying architecture. Extending the system. The architecture we've built here isn't a closed loop. Every layer was chosen for modularity. That means the SharePoint ingestion pipeline at the front is swappable. You can pull out the Graph API connection, the file sync logic, and the routing step without touching anything behind it. If you replace them with a Nextcloud WebDAV connector, a Google Drive trigger, or an OneDrive workflow, the rest of the stack runs exactly the same. The OCR step doesn't know where the file came from. The vector store doesn't care. The agent never even sees the source system. If your organization moves its document storage or if you're building this for a client on a different platform, the ingestion layer is the only thing you have to change. Multi-language support is just as easy to handle. Mistral OCR processes over 25 languages natively using the same model and the same API call. There is no configuration change required. The vector store is language agnostic because embeddings don't care about the language of the text they represent. Semantic similarity works across language boundaries as long as you use a multilingual embedding model. The only real adjustment for a multilingual deployment is the system prompt. You either write it in the primary language of your users or you tell the agent to respond in the same language the question was asked in. That's a prompt change, not an architectural change. Role-based access is the extension most enterprise deployments eventually need, yet most tutorials completely ignore it. The system we built gives every user access to every document in the vector store. For a single team where everyone has the same rights, that works fine. But for a cross-departmental setup where HR files and legal contracts share the same infrastructure, it's a problem. The fix happens at the retrieval layer. Before the similarity search runs, you filter the candidate pool to chunks the user is actually permitted to see. This filter requires a mapping between the user identity and the document permissions stored in your metadata. You can pull this mapping from SharePoint's existing permission model using the Graph API during the ingestion phase. Building it correctly takes real work, but skipping it and trying to add it later is how organizations end up with massive compliance incidents. The SQL tool is currently pointed at the document rows table for tabular data, but you can extend it to query any structured data source the agent needs. You could connect it to a live database of customer records, a product catalog, or an inventory system. Because the agent writes its own queries, adding a new data source is mostly about describing the table schema in the system prompt. You grant read access through the SQL tool configuration and the pattern stays the same. Vector store scaling follows a very clear path. A single VPS running PG vector handles millions of chunks comfortably for most deployments. When your archive grows into tens of millions of documents across a large organization, Superbase vector buckets provide a dedicated index layer. This offloads the search from your primary Postgres instance. If you go beyond that scale, a dedicated Qdrant instance is the natural next step. Since they are incorporated in Berlin, you get high-scale performance with zero Cloud Act exposure. Every additional tool the agent gains follows the same logic. Whether it's web search for current info or calendar access for scheduling, it's just a new n8n sub-workflow. You attach it to the agent's tool list and describe it in the system prompt. The agent's decision framework scales with the number of tools you give it. Deep dive, research and technical validation. The architecture I've laid out in this episode didn't just come to me in a dream. Every single choice, from the dual-path Graph API to using Mistral OCR instead of native tools, was a response to real failure patterns we see when these systems hit production. We didn't just pick SQL routing or GDPR-compliant deployment because they sounded good. We picked them because the research says they work. This section is about pulling those decisions apart and looking at the evidence that backs them up. It starts with one core premise. The quality of your RAG system depends on your retrieval, not your generative model. This is the hill the entire architecture stands on. When you hand a language model a set of document chunks, its job gets a lot easier because it isn't digging through billions of parameters to find an answer. It's just reading the short passages you provided and summarizing them. While a stronger model might write prettier prose or follow complex instructions better, the accuracy of the answer depends entirely on whether you gave it the right information. If you give a world-class model the wrong data, it will give you a confident lie, but a basic model given the perfect data will give you the truth. Retrieval is the bottleneck every single time. This is why the re-ranking step isn't just a nice extra, it is the primary engine for quality. Our initial retrieval pulls 25 chunks to cast a wide net, which is necessary because embedding similarity is a blunt instrument. Two chunks might use the same vocabulary and talk about the same topic, but only one of them actually answers the user's specific question. The re-ranker is what makes that fine-grained distinction. Research from 2026 shows that RAG pipelines using re-ranking consistently beat those that just pass raw vector results to the model. The improvement in precision is massive because the re-ranker selects the most meaningful evidence rather than just returning things that are topically related. These two mechanisms aren't doing the same job, they are complementary tools that solve different problems. I chose Cohere Re-Rank v3.5 for two very practical reasons. First, it's the only re-ranking model that works natively with n8n nodes, which keeps our workflow from getting messy. Second, it solves the GDPR headache. Because Canada has an adequacy determination under Article 45, moving data to a Canadian processor like Cohere doesn't trigger the usual compliance friction. The European Commission has already decided that Canada's privacy laws provide protection equivalent to the GDPR. This means that for a typical company handling internal documents, the data is just as protected in Canada as it is in the EU. You should still verify this if you're in a highly regulated sector like healthcare, but for most operational use cases, the legal path is clear. Now, let's talk about why we aren't using n8n's native extract from file node for OCR. That native approach fails in three ways that eventually break the whole system. It can't see images inside PDFs, it chokes on complex layouts like multi-column tables, and it fails silently on scanned documents. That last one is a silent killer because the workflow looks like it succeeded, but your vector store ends up with an empty chunk. When a user asks a question later, the system finds nothing and either admits it's lost or makes something up. Mistral OCR fixes all of this in one go. The 98.96% accuracy rate for Mistral isn't just a marketing fluff number. In tests across 1,000 documents, including messy handwriting and complex tables, Mistral consistently outperformed the big players. While Google and Azure scored in the 80s, Mistral stayed near the top. For table recognition specifically, Mistral hit 96.6%, while Amazon TextRact trailed behind at 84.8%. These aren't small gaps. They represent the difference between a reliable system and one that breaks every 10th document. Even if you don't care about handwriting, that accuracy advantage ensures your corporate library is actually readable by the AI. The cost math makes this even more of a no-brainer. Mistral OCR costs about $2 per 1,000 pages, which is roughly 97% cheaper than AWS TextRact. If you have a library of 10,000 documents, a full ingest costs you about $300. Since most enterprise libraries change slowly, your monthly upkeep for new documents will likely be under $10. There is no financial reason to use a weaker tool when the best-in-class option is this affordable. To keep it all within the EU, you can run Mistral through Azure AI Foundry. This ensures your documents stay within European infrastructure and under Microsoft's data boundary commitments, which is the only way to go for strict compliance. On the topic of chunking, the research points to a context cliff at about 2,500 tokens. If your chunks are too small, you lose the context that makes the facts make sense. But if they get bigger than 2,500 tokens, the quality drops because the model gets distracted by too much noise. This is why agentic chunking is so effective. It focuses on logical completeness rather than just counting words. Most agentic chunks land between 500 and 2,000 tokens, which is the Goldilocks zone for retrieval. I know the argument against agentic chunking is usually cost or speed. Every document you ingest requires an extra LLM call to decide where to cut the text. If you were processing 1 million news articles an hour, that would be a problem. But a SharePoint library for a normal company might only see 50 new documents a week. The extra few cents and seconds it takes to chunk those documents correctly is a rounding error. You aren't building a high-frequency trading bot, you're building a knowledge base. The quality gain from preserving the logic of a technical manual or a legal clause is worth the tiny overhead. When we look at the infrastructure, people often ask why we use n8n instead of Azure Logic Apps. Logic Apps is great if you want a purely native experience with managed identities, but it fails the moment you need to do something custom. It doesn't have a LangChain module, so you'd have to write custom Azure functions just to handle the chunking. Plus, the pay-per-action pricing of Logic Apps gets expensive very fast when you're constantly polling the Graph API for changes. By running n8n on a German VPS, we get unlimited executions and full control over the data residency for a flat monthly fee. It's not that n8n is better in a vacuum, but it fits the specific needs of a self-hosted sovereign stack. This brings us to the most important part of the research, data sovereignty. The US Cloud Act is a real risk that most people ignore. It allows US agencies to demand data from US companies, even if that data is stored on a server in Europe. If you use a US-based vector database provider, they can be forced to hand over your proprietary data without even telling you it happened. You can't refuse, and you probably won't even know. By running pgvector on a server you own in Germany, you step completely outside that jurisdiction. No US court can compel a German server operator to hand over your data. We aren't talking about a theoretical risk here. We're talking about the actual reach of federal law. For high-risk systems under the EU AI Act, using a US-headquartered provider is increasingly seen as a compliance failure. Since PG Vector is free and running it yourself costs almost nothing, there is no reason to take the risk. You get absolute sovereignty and better security for the same price as a risky cloud service. We apply that same logic to the Azure OpenAI setup. Microsoft's data zones for the EU ensure that all inference happens within member states. By 2026, the standard advice for any enterprise is to use Azure policy to block any deployments that aren't in these specific zones. This ensures that even the abuse monitoring samples are reviewed by staff within the European Economic Area. It's a simple configuration change that makes the difference between a maybe compliant system and a definitely compliant one. The actual cost to run this entire stack is surprisingly low. A decent Hetzner instance in Germany costs about €15 a month, which is enough to run n8n Postgres and your UI without any lag. If you want to isolate your storage, you can add another small instance for €7. Your total monthly bill for the infrastructure is under €25. Even when you add the API fees for embeddings and queries, a 100-user team will likely spend less than €30 a month total. Managed cloud services that charge per query or per user can't even come close to those economics. Performance-wise, this setup is incredibly snappy. A similarity search in PG Vector takes less than 100 milliseconds, and even with the API calls for re-ranking, the whole retrieval process finishes in about half a second. The user usually gets a full answer in under 6 seconds, which feels almost instant in a work context. Because we run n8n in queue mode, background tasks, like ingesting a massive new PDF, don't slow down the people asking questions. The system handles the heavy lifting in the background while keeping the user experience fast. Every piece of this architecture was chosen for a reason. It isn't about being fancy, it's about being pragmatic. We built a system that is private, EU-hosted, and actually capable of answering hard questions about your documents. Most importantly, it's a system you actually own. You aren't just renting a black box from a vendor, you're building a piece of infrastructure that your organization can rely on for years without losing control of its data. That's the full blueprint. SharePoint as the source, Graph API as the connector, n8n as the orchestrator, Mistral OCR as the processor, Postgres as the memory. It's a private system, EU-hosted and built on infrastructure you control. It's a system that finally answers the questions your people are actually asking. If this episode changed how you think about enterprise AI, leave a review. It helps more people find this podcast. And connect with me on LinkedIn, Mirko Peters. I want to hear what you're building.